If we're not doing a multi-layer perceptron and instead doing a convolution neural network or a more complicated neural network, then there's some choices we need to make. And so as we design our neural network, we had talked previously, let's go back here, about how we need to identify the type of network. So a convolution neural network, recurrent, we're going to need to decide on how we're going to prepare our data, the size of our data set, how we're going to split the training and testing, how many hidden layers we're going to have, what variables we're going to use for input, what we're trying to get as output. We're going to need to specify the number of repetitions, our epochs, how many times we go through that training data, and then we'll need to pick an activation function. And in our previous video, we talked about different types of activation functions. Now, as we're getting into designing our neural network in more detail with Keras, what we want to do, stop moving around, is to specify our core layer as well as our convolution layer, and then our pooling layers, and then we have some additional layers if we have, for example, recurrent neural networks. So let's start here with our core layer. So we need a way to input our information. And let's look at a CNN where we are doing image recognition. So when we input our information, we're going to need to specify how it's being inputted. If it is going to be a MLP, we're specifying how many variables are in this regression model. If we are doing a CNN with image recognition, we need to identify that our numbers are 28 by 28 pixels, that it's not three-dimensional, that our data is being inputted as a float 32 or an integer 32. So we need to have it identify how the data is being inputted into the model. We have dense, which is implementing our operations, and this is going to be tied to our activation functions. We're going to specify the activation types themselves. If we are dealing with text, then we're going to have an embedding layer where we need to convert our words into vectors. So we're taking words and turning them into numbers, right? We can have masking layers. So if we're dealing with text, not all statements are the same length. So we're going to have to do things like padding to make sure that all of the statements, if we're doing reviews, if we're looking at reviews, we're going to have to make sure they're all treated as the same length. And so this would be a masking layer. And then we have Lambda. We can add a custom layer for other types of transformations of data. So when we construct our neural network, we would start with our core layer with our input. And then if we're doing a convolution neural network, then we would specify that convolution layer. So we're going to create a kernel function to represent the relationship between data points and nearby data points. If you are looking at data in terms of time, you're going to use a 1D layer. This would help with forecasting models, and you could represent lag effects and time. When you're dealing with text with natural language processing, we can represent the relationship between nearby words by using a one-dimensional convolution layer. So the idea between a convolution layer is that you have a function that is creating a convolution matrix. So we're representing our individual data points coiled or convoluted, so that we're representing the impact of nearby data points in time or order if it's one-dimensional. If it's two-dimensional, now we're talking about representing relationships between pixels and nearby pixels in an image, which can be used to help, sharpening, blurring an image, masking. So if we think about, the Apple stickers where you can take a picture or part of a picture, you can pull the dog out of the picture and turn him into a sticker. This is going to be here, this two-dimensional convolution layer. And then three-dimensional is used for three-dimensional objects. So if we are doing image recognition, and this is the part my face is covering up, we would start with our input layer, bring it in, and then we would do a convolution layer to look at, for this would be 2D here, the relationship between pixels and nearby pictures in the image. So we're looking at a feature map, we're identifying lines. The next step in the process is what is called max pooling. And so we have a pooling layer. This allows us to downsample by taking some maximum value for an area in each dimension. And we're going to then scale images to a similar size, reduce the amount of data, simplify from what we've learned. We can also have average pooling. So we're going to again downsample or reduce the variability to reduce the computational complexity. And in this case, by taking the average value instead of the maximum value. So you're saying, okay, here's an area, here's a bunch of pixels. Let's take the average value of those pixels with kind of the average color of the pixels around it. There's a number attached to that, right? So the color gradient 1 to 255, we would get an average. Or the one that's the max pooling would look at the pixels around it and get a maximum number if it's 1 to 255 for the colors that are around it. So we're simplifying and reducing down the variability here by summarizing a group of pixels. And so that's what we have here is our input. We're looking at our feature map. We've identified a bunch of lines. We're going to reduce the variability by simplifying the pieces that are around it. If you do global max pooling, then we're downsampling by taking the maximum value for the entire input in a dimension. You can use this when you're converting between hidden layers and output. So we're then trying to make inference from what we've collected from those hidden layers. And then there's also a global average pooling, so downsampling by taking an average value for the entire input, again moving from hidden layers to output to convert your feature map into a confidence map. What's the probability that this is a picture of a dog or that this is the number 2? So the global ones are when we are transitioning from our final hidden layer to our output. The max pool and average pooling are used to kind of help summarize what we've learned from running creating that convolution layer. So we have our input convolution layer that I would identify kind of lines, then we max pool, then we have another convolution 2D layer, and then a max pool, and then another feature map convolution 2D level, and a max pool. So multiple levels where we are each time looking at the relationship between data points and nearby data points. And then we are kind of summarizing that with these pooling efforts. So in the convolution neural network, then what we would do from there is prepare it for output. In recurrent neural networks, you would have other layers like deciding how much information is retained over time for your recurrent neural networks. You can have long, short-term memory. And then your bidirectional layers determining how much the weights are for going backwards and forwards. There are other layers that you might encounter. Batch normalization, so we can standardize elements. So we have a mean of 0, standard deviation of 1. This can help make the neural network perform faster, be more stable. You might also decide to drop some of the information. So you could have a set percentage of activations that are set to 0. This helps to reduce overfitting during training, similar to kind of lasso regression we talked about in our previous videos. We can also have layers that flatten, that convert multidimensional elements to one dimension, and that can be used to help transition here at the end with our images, for example, when we go from all these convolution layers to a fully connected layer, which is telling us, you can't even see this, I'm pointing at things that are behind my head, where we are showing, now we're translating all of these pieces into what's the probability this is a picture of a dog or a person or the number 2. And so these are fully connected layers to help us transition to that final output. So in the videos that we're going to do next, we're going to look at how do we actually do this in Python? How do we choose these different layers? So we'll look at some examples of each. And then to wrap up our discussion here, let's just look at some of the metrics we can use to assess our artificial neural networks. If we are dealing with one that is a binary classification, we can look at accuracy. We can look at precision, the percent of all positives that are true, recall, the percentage of labeled positives that are actually true. We can look at the area under the curve or the receiver operating characteristics curve. We talked about those when we talked about some of our classification models. So those are all used when we have binary classification. There's also something called categorical cross entropy that we can use to find the difference between actual labels for categories and predicted labels. So it's an accuracy for multiple labels. And then if we are looking at ones that have interval or ratio type outputs, then we can use mean squared error, root mean squared error, MAP, and R squared, just like we've used in our forecasting models and our linear regression. So we can choose metrics for how to assess the model in addition to choosing all of the hyperparameters and components of the neural network itself. So in the next couple of videos, we're going to do that, and we're going to apply it to a number of different situations. So one thing before we go is that when you are looking at your metrics, when you're looking particularly at the mean square error or root mean square error, and we're deciding on the number of epochs, how many times we go through, one thing we're taking into consideration is the gradient descent. So I'll just go through here. When we talk about gradient descent, we're looking at, as we loop through each epoch, we are trying to learn and improve the model, and we do that by tuning these hyperparameters to help reduce the loss function. So try to get that mean square error lower. Now what we're doing is we're looping through many times, hoping that as we explore a random walk and go through it different ways, that we're searching for the combination that gives us the lowest error. So with gradient descent, we're estimating when error, the difference between our predicted value or label and the actual value or the label, is at its lowest. And our concern, of course, is that we get stuck in a local minimum rather than a global minimum. So the network itself is searching for the combination that gives the lowest error by exploring different weights for the variables and the hidden layers. And if it is a convolution neural network that is forward, it is going to adjust those with back propagation. After it goes through, it adjusts the weights and goes back through again. So one way to keep it from getting stuck in these local minimums, like here, instead of the global minimum here, is to have more epochs, right? To go through more times, because each time it's going to take a different path. But it's also why we need to monitor the mean square error as we go through, because each time it is trying to adjust those weights in order to get it even lower. So we need to recognize that we need those metrics to help improve the model and have it adjust the weights to get it lower, but also that we need to go through the whole process multiple times, because it's quite possible that it'll go through and find something that minimizes the mean square error and think it's found a solution, but it's simply in a local minimum as opposed to a global minimum. So as we go through more times, then we're able to go different routes and find the global minimum, making the accuracy much larger. It also makes your model more stable, because if you then run it again, it stops changing